We've mentioned a variety of tools that can be employed in classes here in the College of Natural Sciences. There's a lot of theoretical framework that suggests that these kinds of tools or strategies just like them could be very effective in terms of student learning. A quote that kind of summarizes my thinking about teaching changes the ballgame from thinking about how it is that I teach to how it is that students need to learn. Our job as instructors could be thought of as activating the learning of students in our classes, and thinking about how it is that we train them to take on new challenges or take on skills in addressing challenges that they don't currently have. We all know that that's an iterative process in our research kind of learning, and it's an iterative process in classroom learning. Our job then is to assist the rewiring of the brains of students. There are some experimental psychology results that kind of support the kinds of strategies that we've talked about, and that is done in a number of different research groups, but some of the work done by Bjork and collaborators at UCLA suggests that the learning process is actually aided by introducing challenges or barriers to students, and those barriers, that kind of puzzle solving, contributes to an overall pattern of long-term learning, kind of metacognition that learning theorists talk about, versus short-term memory recall and the ability to just regurgitate something on a test. It's an interesting notion that if we think about our classes as ultimately having a goal of long-term learning, there are different strategies that would be more effective than the requirement that our students be able to do well short-term, as in on a midterm test. A very simple result from experimental psychology supports the idea of what it is that what strategies work well for long-term learning. A psychologist in a certain research group asked participants to divide up their study time, a classroom hour, in several different patterns. In one pattern, students in the participant group were asked to study a particular piece of material, a word, a sentence, or a paragraph, in 4 consecutive 5-minute study periods. So for each of those study periods marked S, the students were given the same information and asked to memorize that information. At the end, they would be given a test. They'd be given the same test a week later to see how good their long-term retention is. A second treatment group was not given all 4 blocks of time to study. Instead, they were given 3 blocks of time to study and 1 test opportunity, a chance to actually show how much they got. A third study group was only given 1 opportunity to study and then tested over and over and over again, 3 times over, on that material. And again, they were tested at the end of a short period and then at the end of a week to see how long they retained the material. Not surprisingly, the folks that studied over and over and over again and then were only tested once did very well on the short-term test, the one that was taking place right after this 4 consecutive blocks of time. But the group that actually did measure retaining that information a week later was the group that only had 1 opportunity to study and then was tested over it over and over and over again. Such results are found in numerous contexts, either in just pattern recognition type things or cognitive or induction-based exercises. The act of testing should actually be thought of not just as a form of assessment, but as a teaching tool, an opportunity for students to better themselves and rewire that parts of their brain that need to make connections in order to answer a question. It's also true that these kinds of strategies of frequent testing and frequent assessment aren't the most popular with students, and it's often the case that when you ask the students honestly, how did you feel about the process, students gravitate toward the opportunity to privately go and study or memorize, as opposed to the chance of asking for the chance of being assessed over and over again, which is inherently a stressful experience and putting the student in the crosshairs. So it has to be appreciated that the testing can be helpful, but helping the students understand that that's actually going to help them be successful long term requires some individual coaching or coaching of the class as a whole. There's a visualization of this kind of general idea about what it is that leads to long-term memory or understanding of material. And the shortest term or the shortest form of retention comes from just reading in books or hearing material in lectures and or seeing things presented visually, like on transparencies or in PowerPoint demonstrations. More long-term memory comes about when one sees exhibits or demonstrations or multimedia simulations, and yet even more long-term retention happens when students are asked to discuss or explain to others exactly what it is that they're working on, or even better yet, enact the experience or the process of solving the problem or simulate the real experience, and even better yet, do the real thing. That is, when we work in the lab, we tend to remember the outcomes or the lessons of the lab. Or when we can try to simulate that process in inquiry exercise in class, we tend to come as close as we can to actual research in terms of mastering long-term retention. Which isn't so hard to imagine. It's been ever since Confucius that we had the phrase, if I hear, I forget, if I see, I remember, but if I do, I actually understand. Students in classes here at the University of Texas have been asked what it is that's the most effective for them in terms of their own learning. And in a flipped classroom design where there were learning modules available to the students, as well as weekly worksheets or homework problems, as well as just the large repository of video clips, as well as things like the classroom lecture or the TA and professor's office hours, as well as an online textbook free to the students and having the same materials as were in the video clips and learning modules. Students responded overwhelmingly with the kinds of things that were really helpful to them. First of all, they found the learning modules to be very, very helpful. Notice that more of them found the learning modules to be helpful than the video clips to be helpful. The video clips are actually the pieces of content that are in the learning modules. However, learning modules are different from just video clips in that the learning modules also have assessment questions in them. They are opportunities for students to grapple with that material that they just saw in the video clip and see if they understand how to use it in answering the questions. The students themselves found the learning modules as enabled by Quest to be more effective than just offering a repository of video clips. The most effective tool that students pointed to as an effective resource for their learning were the office hours. That suggests a real change in how we think about our classes, because an effective class could take place without a lecture altogether. You could have a class offered with an instructor creating the content material and then structuring lots and lots of pods of students working in learning communities in the form of office hours and TA tutorial sessions. That may not be what we choose to do, but notice what the students point to as the most effective. That's not to negate the value of a lecture class or the classroom hour altogether. In fact, still many students point to that experience as valuable in their learning. But just notice how instrumental it is to have the individual attention and the directed opportunity to answer questions with your TAs or your peers about problems that you're working on. It's also worth pointing out that these blended courses or flipped class designs actually result in better mastery of material. And while several studies have been done, studies using data here at the University of Texas is perhaps instrumental because it's now a study derived from a Quest-based hybrid course. The Statistics 302 course was taught for many years on this campus, and in its many-year history, there have been a number of successful instructors doing a lot of different innovative designs. But once the blended course design was implemented with Quest-based learning modules, notice that the number of D's and F's actually dropped by a factor of 2, and the same content resulted in better mastery by the students when the content presentation was happening through Quest rather than by lecture class. These kinds of findings are not unusual to just us at the University of Texas. There are entire communities of education researchers working and finding the similar results. And within many disciplines, there are entire research groups dedicated to designing curricula around these kind of learner-centered strategies. Within chemistry, for example, the National Science Foundation funded a multi-university project called Process-Oriented Guided Inquiry Learning, Essentially, it's flipped classroom design with lots of in-class puzzle problems. That program, otherwise known as POGL, has numerous workshops all around the country to facilitate faculty who want to implement something that looks an awful lot like a flipped class design or an in-class inquiry design. In the physics community, author Eric Mazur is well known for his book Peer Instruction, which has lots of resources for faculty who want to implement in-class puzzle problem solving as the form of instruction that occurs in class. And then the outside of class experience is done either through textbook learning or online database learning or flipped classroom type designs with videos and text. That's left to the instructor. However, what Mazur has done is show us as faculty that in-class puzzle problems can be very effective in terms of allowing students to master the material.